moment of a couple. People normally just call it a couple. But really what we're calculating is the moment produced by a couple. And a couple is two equal and opposite forces acting at a distance. For example, if you've ever seen any kind of bolt that you turn with like a spanner tool, bolt like you used to have to do this all the time. So you put one little notch in there, one thing in there, and then you turn it by when you turn the spanner, it applies a downward force there and an upward force there. They're equal and opposite forces. So if that force is the opposite direction and the same magnitude as that other one, that's a couple. And what we're going to see is that for a couple, produces a moment that doesn't depend on the about point. It's the same no matter what the about point is. So you can think of a couple as like just a pure moment, okay? No matter what your about point is, you can just add this pure moment onto the rest of your moments. Okay, so that's surprising. It's the only thing that does that. And it's an explanation for why we're going to treat couples the way they are when they, what a couple really is these equal and opposite forces, but we're always going to just treat it like you're adding on a moment of 400 Newton meters or something. Okay, you're just adding on this number. Where does it come from? And so where it comes from is the two equal and opposite forces, but that nature makes it so you can treat it like just this couple of its own. Okay, so let me show this. Don't believe me? Prove it, thank you. So here's just some arbitrary body. And here's some about point. And we'll apply a force F I'll call, yeah, just F. I'll apply that at a point P1. And then somewhere else on the body, I'll apply an equal and opposite force. So those are parallel, but it's going the other direction. That's also F. And the point where that force is applied is P2.
And just to be careful with the notation. So those magnitudes are the same, but if you're representing this in components, that vector I'm going to call negative f. Okay. All right, so we're going to calculate the sum of the moment produced by f and the moment produced by negative f. Okay. So the row vector for f goes from the about point to here, right? That's I'll call that row 1. And the row vector for the negative f force is like this. I'll call that row 2. And what do we expect to happen? So I'm going to set this up as, the total moment of this couple is equal to row 1 crossed with f plus row 2 crossed with negative f. And what would show that this moment is going to be the same no matter what the about point is? How would we see that in this proof? Well, we haven't seen it yet, but what are we looking for to prove that it doesn't depend on where A is? What we're going to see is that the value for A, the components of A, are just going to disappear from the calculation. Okay, so like to start with, they're in there. This row 1, you can write this as P1 minus A crossed with F plus the quantity P2 minus A crossed with negative F. Okay, so they're in there. If you looking at it right now, change the value of A, change where that about point is, the coordinate of that about point, most likely will change the answer. What we're going to see is that those cancel out. A isn't in there at all. So it doesn't matter what the numerical value of A is. Okay. Does that make sense? That would show us that it doesn't depend on that A. Okay, so you can distribute multiplication out with the cross product. So this gives you P1 cross A, P1 cross F minus A cross F. That's the first one. And then add on the second one that says P2 crossed with negative F minus A crossed with negative F. And now you can pull out the negatives. So P1 cross F minus A cross F minus P2 cross F plus A cross F. And now you can see where that cancellation happens. And so what you get is the cross product of this difference, P1 minus P2, and F. So what we saw is that the moment of a couple is the same no matter what A is.
So when we see couples and problems, we're just going to represent them as a moment, because if a couple produces a moment of 450 Newton meters, then no matter what you choose as your about point, that's what it's going to be. So we'll just put it on there as just a moment and nothing else. It doesn't produce any force. You don't have to worry about the forces because they're equal and opposite. They cancel out. Okay. So the way we'll represent, so the representation of couples in 2D will usually be like this. Or this. Okay, so that's saying clockwise or counterclockwise. But remember, a moment is really a vector. So even though it's shown like this, that would really be a vector in the positive z direction. This would be a vector in the negative z direction. And in 3D, these will be represented as vector components with double heads. So you'll see stuff like this. Heads for the two forces, I guess. And you won't always have all three. So if you see something like one like that and one like that, so let's say we have this body, a disk, and let's say that there's an unknown force over here, an unknown force vector. I'll call this force vector F1, 2, 6. And then over on the other side, let's say there's a force with a known direction. It has a magnitude F2, and it makes an angle of 30 degrees with the horizontal. And then down here at the bottom, there's a couple applied. Now that couple really is two equal and opposite forces, but I'm just going to represent it as a pure moment of 450 Newton meters. Right. And I could have, an equivalent way to write this would have been to have it look like it's going the other way. And, oh, actually, let's make this a negative. Yeah, I could have made it go the other way with a negative on it. But this symbol, people use this a lot for two-dimensional statics and two-dimensional problems. That's sort of misleading about what this is, remember. Remember that a moment is always a vector, okay? And so to think about the direction of that vector, you have to use the right-hand rule with that rotation, okay? So if it's going this way, that's a moment in the positive z direction coming out of the board, okay? This one, and then with the negative, that makes it with the other direction. And let's, so the counterclockwise is positive, and then the negative on the number says, you know, that it actually goes the other way. So that says that as a moment vector, that is 0, 0, negative 450. On which? On the couple?
At the moment, you have a counterclockwise arrow
Right.
that indicates positive direction.
Yeah, so that's the same as like if I had written this with a negative, you know, I said it's going this direction and this was negative F2, that would be the same thing as F2 going this direction. Because if you multiply any vector by -1, it switches the direction. Okay, think of that as like something you're multiplying to a unit vector. Okay, so let's calculate what are F1 and F2 if this object is in equilibrium. And I'm going to do this calculation. When you do this, you can choose any about point you want for moments. I'm going to choose my about point here. Okay, that's going to be my A. So I'm going to set up this table with row, force, moment. And we need a radius for this. Let's say that the radius of this disk is 0.5 meters. Okay, so I'm going to start with the force F1. The row vector goes from the about point to where the force is applied. Okay, so we need to figure out a vector that goes from A to where F1 is applied. Okay, so how do you get from A to F1? You go 0.5 meters down and then 0.5 meters over, right? That's the negative y direction, negative x direction. So that row vector, if I do it in 3D, is negative 0.5, negative 0.5, 0. With me on that? And then the force vector is F1x, F1y, 0. And so the moment produced about A is negative 0.5 F1y plus 0.5 F1x. Yes?
Do you typically not write the moment as a vector?
That is a good, I do want to right now. Thank you for. So pretty soon I'll start writing it as a scalar just to save time and whatever. But yes, I did want to do that. So it's 0, 0, and then the z component is negative 0.5 F1y plus 0.5 F1x. Okay, that's what it is as a vector. Any other questions? Okay, now let's go to the other force. So what's the row vector for this force F2? So we want the vector that goes from A to where F2 is applied. Yeah, so positive 0.5 for x, negative 0.5 for y, and then 0 for z. The force vector yeah, exactly. So if this is the coordinate system, and that's the vector, it has a magnitude of F2, and we know that this is 30 degrees. So from the positive x-axis, that's 180 minus 30, so 150. And so this force vector is negative 0.866 F2, positive 0.5 F2, and then 0 for z. Then take the cross product of those two, and the moment is 0, 0. And then for z, it's 0.25 F2 minus 0.433 F2 and so that is 0.183 negative. Is that right? F2. Okay, and now we get to the couple. And for the couple, we don't care about these. It's not going to produce a force. And we don't care about its relationship to any about point because it produces the same moment around any about point. All we care about is the couple, and the answer there is 0, 0, negative 450.
So that's for the couple there?
Yes.
And the second part was for force two?
For
The second variable,
this stuff?
yeah.
Yeah, we don't care about the row vector because
Right, that's for the moment.
yep. And then for force, we don't care about that because a couple is always equal in opposite forces, so they add up to 0.
The second row, that's for friction.
Oh, yes. Oh, I see what you're saying. Yes, that's F2. Yep. Yeah, that's F2, and this is the couple, the 450. And now we can go to Newton's second law. How many Newton's law equations are we going to get here? 3. It's a two-dimensional problem, so we're going to have 2 useful equations for Newton's second law plus 1 useful equation for the moment equation. Okay, so Newton's second law first. Okay, so do we expect to be able to solve this? Yeah, because how many variables do you have? 1, 2, 3. So 3 equations, 3 variables, as long as nothing funky happens with linear multiples, we should be able to solve this. Okay, so Newton's second law, what we're going to do, this is what's nice about this table. We're going to take all these and just add them all up, and that's the left side of Newton's second law. So we have F1x, F1y, and I'm going to leave off the z's because the z's are always going to be 0 for a two-dimensional problem. And then plus negative 0.866 F2, positive 0.5 F2, And that's everything. So since it's an equilibrium, those add up to 0. And then for the moment equation, rotational Newton's second law, I'm going to take all these and add them together, and that gives me the left side of the rotational equation. If we did it for x and y, for each one, we just get 0 equals 0. You know, that doesn't help us at all. So I'm just going to write down the z equation. So we have negative 0.5 f1, f1y plus 0.5 f1x minus 0.183 f2 minus 450 is equal to 0. You could solve this by substitution, but I'm going to write out an augmented matrix and we'll do it that way. So we have 3 equations. That means 3 rows, 4 columns. And the order I'll go in is f1x, f1y, f2, and then the constant. And these are equations 1, 2, and 3. The first equation is the x component equation for Newton's second law. So f1x's, we have 1. f2's, we have negative 0.866. And the other 2 are zeros. The second equation is the y equation from Newton's second law. We have f1y, we have 1 of those. f2, we have 0.5. And then zeros. And then the third one, f1x's, we have 0.5. f1y's, we have negative 0.5. f2's, we have negative 0.183. And you have to move the constants to the other side, so the constant is positive 450. And if you do reduced row echelon form, you get the same size matrix back. Where these are 1s and 0s like this. And the answers are going to be given in the order f1x, f1y, and f2. 779.4, okay.